Hi everyone, welcome to our next video for week 5. And today we're talking about hypothesis testing for two means where the population standard deviations are not known. Just like hypothesis tests for a single mean or confidence intervals for a single mean, we know that when we don't know the population standard deviation, we need to use a student t-distribution. So these are going to be t-tests. Just like the t-tests we've talked about before, you're looking up your critical values in table F, or you're using inverse t distribution on your calculator or computer. Much like the z-test for two means, if we are assuming that our null is an equality statement, so if our null looks like this, if we're not given values for mu1 and mu2, that's going to be 0. But again, you're not going to encounter a situation where that's not true in this class. And I'm assuming we're all using calculators or computers. And so we're using those same function calls we use for the p-value method to get that test value. For a TI-84, that's going to be in the stats test menu. And you want option 4 to sample t-test. And then the prompts will show up. If you are in GeoGebra, it's a t-test 2, a little bit easier. And then it wants all the information for sample 1, and then all the information for sample 2. And then it wants tail, and then you need to type in false. This has to do with pooled versus non-pooled data. We're assuming we're not pulling it. We're looking at independent samples. It gets a little bit more complicated when you start looking at pooled data, and we're not going to do that in this class. If you encounter that in the field, you should see that in a later statistics or topic-specific course. Okay, just like last time, we're going to do a couple examples so you can see how this works in practice. So example 1, a researcher wishes to see if the average weights of newborn male infants are different from the average weights of newborn female infants. She selects a random sample of 10 male infants and finds the mean weight is 7 pounds, 11 ounces, and the standard deviation is 8 ounces. She selected a random sample of 8 female infants and finds the mean weight is 7 pounds, 4 ounces, and the standard deviation is 5 ounces. Can it be concluded that at alpha equals 0.05, the mean weight of the males is different from the mean weight of the female? Assume that the variables are normally distributed. So this is another example where they've thrown all of that information at us and not put it in a table. So we need to parse through what's being asked and what's being given. So the question down here at the bottom is, can it be concluded? So we know that's one of those possible key phrases for a hypothesis test. We also see mean weight of males, mean weight of females. So we know it's a test for a mean, and we know that we're comparing two. So this is definitely a test for two mean. We just need to figure out, is this a z-test or a t-test? A test for two means, and the question is z or t. And if we go back through this problem, we're given a whole bunch of information for male infants. So 10 male infants, mean weight is this, standard deviation is this. Notice that standard deviation is given for this sample of 10 males. So even though they don't say it, that's an S, not a sigma. So they are giving us a sample standard deviation. If we read for the next sample, it's a sample of 8 female infants. So that's our second sample with a sample mean weight of 7 pounds, 4 ounces, X bar, and a sample standard deviation of 5 ounces. So that's another S. So if we're given S instead of sigma, we know that this is going to be a t-test. We also know down here, we are given our alpha value. We want to run this test with a 5% level of significance. Okay, so let's clear this out of the way so we can make room for our table. We know we want to organize our information before we run our test. So we're given a sample size, a sample mean, a sample standard deviation, and we're given that for male babies and female babies. Oops, not for male, female. So I'm going to call this group 1 and group 2 because that's the order they appear in the problem. I'm going to make my table here. So we know the male column is in orange. I underline that in orange. So sample size of 10, sample standard deviation of 8. That sample mean is problematic. This standard deviation is 8 ounces. The mean weight is in pounds and ounces. I know that my mean and standard deviation need to be in the same unit. They need to be measuring the same thing in the same unit. So I need to convert that mixed units, pounds and ounces, into ounces. So I happen to know 1 pound is 16 ounces. So if you multiply 7 by 16, you should get, I think, I want to say 112. And then you add 11, you get 123. And then same thing, if you do 16 times 7, you get 112 plus 4 is 116. So I'm going to write those values down as the values for the mean. So that 7 pounds, 11 ounces in orange is going to become 123 ounces. And then we're going to do the same for the female column. That was underlined in green. So 8 female infants. The mean weight is 7 pounds, 4 ounces, which is 116. And they had a standard deviation of 5 ounces. And then I'm also going to jot down here, I know my alpha is 0.05. The very last thing before I start writing my hypotheses, there's that keyword different from. So we do know when we write our hypotheses, our alternative is a not equal to. So I'm going to set up our frame for the p-value method because we know it always looks the same. That same 4 steps, regardless of the type of test. So hypotheses and claim, p-value, decision, conclusion. In this case, we're doing claims about means. So mu1, mu2, mu1, mu2. We know that keyword different. Alternative is a not equal to, and that's the claim we're testing. And then I do the default null of equal to. So next, we're going to go ahead and use a PI84 for this first test. So stat test option 4, 2SAMP T test. 2SAMP T test. I'm going to copy down that function name. It's part of showing my work. 2SAMP T test. And then it's asking for X bar 1, 23. S1 is 8. N1 is 10. And then the same for group 2. So the mean for group 2 is 116. Standard deviation is 5. Sample size is 8. And then the tail is not equal to. And we're going to scroll down, make sure it's not asking for anything else. And And it is, it's asking pulled or, and then yes or no. And this is similar to what it's doing in GeoGebra where it's asking true or false. So in GeoGebra, you're going to put false. For the TI-84, you're going to put no. That's the default. This is not bool. So let's go ahead, type our values really quick. We get a p-value of 0.0383. 0.03825 rounds up to 3. Before I move on to our decision, I'm hoping you notice when I write those values out in a list, before I type them in my calculator, it does make the calculator work go quicker. So this is good practice, not only to show others what you plugged in the calculator, but it's going to help you move a little bit quicker if you do that. For step 3, we're comparing that p-value to our alpha of 0.05, and 0.38 is smaller than 0.05, so that's a less than or equal to, and that tells us we're going to reject null. So our last step, let's take that rejection decision and phrase it in terms of what the problem's asking. So starting with step 3, when we reject the null, that is providing evidence. So there is evidence 2, and then we look back to step 1. The alternative is the claim, so we're supporting that claim. And then we go back to the problem to summarize that claim. And it says, can it be concluded that the mean weight of males is different than the mean weight of females? Specifically infants, but I'm using that wording from that last question down at the bottom, and that's okay. So there is enough evidence to support that claim that the mean weight of male infants is different than the mean weight of females. Okay, I'm going to do example 2 with you, and then I'm going to have you guys try example 3 on your own. Let's move on to example 2. Says the average amount of time boys and girls aged 7 to 11 spend playing sports each day is believed to be the same. The study is done and data are collected with results displayed in the table below. Each population has a normal distribution. Is there a difference in the mean play amount of time boys and girls aged 7 to 11 play sports each day? Test at the 5% level of significance. In this case, they were nice. They did provide us with the information in the table. So that's helpful. We are going to go through the word problem and parse what we're given. So let's go ahead and take a look at that word problem. So it says, is there a difference? And then it says in the mean amount of time, blah, blah, blah. Is there a difference tells me 2 things. 1, not equal to, and 2, we are testing a claim. The claim is there a difference? And then it does say in the mean amount of time for boys and girls. So I'm testing a claim about a mean, and I'm testing a claim about a mean for 2 different groups. The other thing is they do give me my alpha, a 5% level of significance. That's in decimal form 0.05. In the table, looking at what I'm given, I've got 2 groups, girls, boys, 1 and 2. I'm given my sample size n, my sample mean x bar, and then a sample standard deviation, s. I know when it's s instead of sigma, I'm running a t-test. So this is a t test for two means. So I'm going to go ahead and set up the frame for our p-value method. Starting with our hypotheses, claims about two means. So mu1, mu2, mu1, mu2. We look for the one of those symbols in the word problem, and we know that specifically they say difference, and inequalities go in the alternative. Default to equal to for our null. Next step, we go ahead and we grab, and I'm sorry, I just had a total brain fart. We grab our calculator. My poor little brain can't function today. For this one, I'm going to go ahead and use GeoGebra. So let me write out what that function is looking for first. So we know for GeoGebra that that function call is called tTest2, and it asks for a few things. It's going to ask us for the sample mean for group 1, and then the sample standard deviation and sample size, and then the same thing for group 2. So X bar 2, S2, N2, and then it's going to ask for the tail, and then we need to tell it false. So let's go pull that information from the table. We know X bar 1 is 2, S is 0.866, and N is 9. For group 2, the sample mean is 3.2, the standard deviation is 1, and that sample size is 16. The tail from the alternative is not equal to. GeoGebra needs quotation marks around it. We always say false, or data is not full. So let's go ahead, pull up GeoGebra and enter that information in. I'm going to go ahead and erase this mess so we can see clearly here. Notice as soon as I finish typing false and it senses a complete function call, it pops up those values. So we get a p-value of 0.0054. That second value, by the way, is the test value. The fact that it's negative tells us that sample 1 is less than sample 2, which we can see very clearly from the table. 2 is less than 3.2, so it makes sense that we get a negative critical value because sample 1 is less than sample 2. And the fact that our p-value is really small and that critical value was or test value rather, was a big negative, tells us that that difference is statistically significant. It tells me that when I get to step 3, I am going to reject the null. Our p-value is very clearly less than or equal to that 0.05 alpha that we have. So we should very firmly reject that null. And then all we do is summarize our conclusion in terms of the words from the problem. So we reject, that means we are providing enough evidence. And then our claim is the alternative, so we are supporting the claim. And then we fill in what the claim is. So the claim is that there is a difference in the mean amount of time boys, if I can spell, boys and girls aged 7 to 11 play sports each day. And again, for those of you who are not big fans of words, oops, that is not what I meant to do there. Nope, I guess it's just 11 from now on, or yellow from now on. Yellow. Apparently, no, it's just yellow. That's okay. I learned something new today. Where was I going with that? Oh my gosh, I completely had a brain fart. Oh, the wording. I pulled that wording directly from this last sentence, or second to last sentence. The community group believes that oh my gosh, I'm on sample 3 or example 3. That's why that looks weird. Okay, sorry. Mr. J is having a brain fart. Let's fix that. There we go. That makes more sense. Thank you for bearing with me. I pulled it from that last sentence. Is there a difference in the mean amount of time boys and girls age 7 to 11 play sports each day? So that ended up in the wording down here. Don't overthink, right? You look at whether you reject it or not. So is there evidence? Is there not evidence? And then you look about support or reject. And then you just state the claim as it's stated in the problem. Okay. I'm going to clear this. I'm going to pop up example 3. Pause your video. Go ahead and work through this. Again, I'd encourage you to make a table since you aren't given one. And then when you restart the video, I will have the solution for you to check your work. Okay, so example 3. Studies done by a community group in 2 neighboring colleges to determine which one graduates students with more math classes. College A samples 11 graduates. Their average is 4 math classes with a standard deviation of 1.5. College B samples 9 graduates. Their average is 3.5 math classes with a standard deviation of 1. The community group believes that a student who graduates from College A has taken more math classes on average. Both populations have a normal distribution. Test at a 1% level of significance. So a few things. First, they give us a claim. The group believes that blah, blah, blah. And then they say test. So they're giving us the claim, asking us to test it. That tells us this is a hypothesis test. They also consistently use the word average. College A has taken more math classes on average. We're given the average for College A, the average for College B. So I know this is a hypothesis test for specifically 2 means. The decision is then T or Z. And because we're given sample standard deviations, we're going to use a t-test. I summarized the information given to us in a table, College A, College B. You'll notice I didn't label them 1 and 2 because A and B are perfectly reasonable labels. So for our hypotheses, the null is that the mean for A equals the mean for B. And then the alternative is that the mean for A is greater than the mean for B. They say that College A has taken more math classes, so A should be greater than B. For step 2, I used the TI-84, so 2-stamp t-test, and then the sample data for group A and the sample data for group B. This is a greater than, and for pooled, we select no. And when I ran that, I got a p-value of 0.1928, which is significantly bigger than our level of significance of 1%, 0.01. So we're going to fail to reject that null. These samples are not different enough that I feel confident stating that it is likely that the populations they were pulled from are different. So our summary says there is not enough evidence to support the claim that graduates from College A have taken more math classes on average than graduates from College B. Okay. If you have questions on what you've been seeing in video, feel free to email me or send me a message in Canvas or drop by my office hours. Otherwise, I will see you in our last video.